Today, we're going to be talking about assembly language and the power of x86 assembly code. Introduction. So, we're going to take a journey through the history of x86 assembly, explore its uses, and understand the benefits of actually using assembly language, which is very complicated, so you must be wondering why we would use it. Going over some history, x86 assembly code is a low level programming language used to write programs that directly interact with the hardware of the computer. The assembly x86 language was first introduced by the Intel Corporation in 1970s, and quickly became the most popular assembly language used for personal computers. The first microprocessor to use the x86 architecture was Intel and their Intel 8086, which was released in 1978, and it had a 16-bit data bus and could address up to 1 megabyte of memory. Since then, the x86 architecture has evolved to become one of the most widely used architectures in the world. Some uses. x86 assembly code is used for a variety of purposes, including operating systems. Many operating systems like Microsoft's Windows and Linux are written in x86 assembly code. This is because the low-level nature of the assembly code allows for precise control over the computer hardware, which is necessary for the operating system to manage system resource efficiently. Another use is device drivers. Device drivers are software programs that allow operating systems to communicate with hardware devices, such as printers and scanners. These drivers often need to interact directly with the hardware, making assembly code an ideal choice for writing them. Another use is embedded systems. Embedded systems are computer systems that are designed to perform specific tasks, such as controlling a machine or monitoring a process. Assembly code is often used to write software for embedded systems because it allows for precise control over the system's hardware. Now, going to the benefits of x86 assembly, it offers several benefits including performance. Assembly code can be optimized for speed and efficiency, resulting in programs that run way faster and use way fewer system resources than programs written in higher level languages like C or C++. Control. Assembly assembly code provides precise control over hardware, allowing for more precise and efficient use of system resources. And finally, portability. Assembly code can be written to be portable across different hardware platforms, making it ideal for writing software that needs to run on a variety of different systems. In conclusion, x86 assembly code has a rich history and is still widely used today for a variety of purposes. Its low level nature makes it ideal for writing softwares that need to interact directly with hardware, such as operating systems, device drivers, and embedded systems. Using assembly code offers several benefits, including performance, control, and portability. Now we'll go through the code walkthrough on our rock, paper, scissors game.
Now onto the code walkthrough. This section defines the data segment, which contains static data used by the program. Here we define 4 messages that will be displayed to the user during the game. This next section defines the BSS segment, which contains uninitialized data used by the program. Here we define 2 bite-sized variables that will be used to store the user's input and the computer's randomly generated move. This section defines the text segment, which contains the actual code of the program. We define the global label underscore start, which marks the beginning of the program. This code uses system calls to display the message stored in prompt to the user. It first loads the system call number for write into EAX, the file descriptor for standard output into EBX, the address of the message to display into ECX, and the length of the message into EDX. It then makes a system call using int 0x80. This code uses system calls to read a single byte of input from the user and store it into the input variable. It loads the system call number for read into EAX, the file descriptor for standard input into EBX, the address of the input variable into ECX, and the number of bytes to read into EDX. It then makes a system call using int 0x80. This code generates a random move for the computer based on the user's input. It first loads the value 42 into EAX. It then clears the EDX register using the XOR instruction. It divides EAX by the value stored in input using the div instruction. Since we only care about the quotient, we discard the remainder by setting EDX to 0. We then add 1 to the quotient. Since we want the computer to randomly choose one of the three possible moves, rock, paper, or scissors. Finally, we store the result in the computer variable. This next block of code compares the user's input to the computer's generated input to determine the winner or if the game resulted in a draw. The move AL input instruction moves the value of the user's input into the AL register. Then CMP AL computer compares the value in AL to the value in the computer variable. If they're equal, the program jumps to the draw label. If they're not equal, the program continues comparing AL to the character R, P, or S to determine which option the user chose. This last block of code determines if the user chose an invalid input. If the user did, the program will output a message using move EAX4 to specify a write system call, then move EBX1 to specify std out, move ECX draw message to specify the message to write, and then move EDX6 to specify the length of the message, and lastly int 0x80 to make the system call. Finally, the program will exit.
Hello, my name is Juan, and today I will explain to you our assembly code. Rock, paper, scissors from line 55 to 115. First, we have a procedure, which is rock here. A procedure is similar to a method in Java or a function in C, which you already know. It's basically a block of code that can run multiple times in start. It will increase the modularity and reusability of the block of code. So you can run it multiple times in the code runtime. So here, first, it will compare the rock procedure will compare the it will compare the result of the random number up there to P, which is paper. So yes, you can see the comment here, compare it to paper. It will jump to loose if this comparison is return a true. So basically it return a non-zero statement. It will jump J is basically a condition jumper, so it's only gonna runs if this return a non-zero statement. Otherwise it will go down here, continue running. So it's gonna jump to win if the computer choose Caesar. Otherwise it go to draw. The jump here is basically a jump condition, basically a jump statement. If these two is not true, then it's gonna run this. It's kind of like an else statement. This is an else and this is an if statement. Paper works pretty much the same thing. So it's basically the computer choose scissor. If the computer choose scissor, then it will jump to lose. Otherwise, it's gonna jump to win. And if both of these is not true, it will be draw. Same thing for scissor. So basically, the computer choose rock, it's gonna jump to lose. Computer choose paper, it's gonna jump to win. Otherwise, it will draw. Going down to win. Here we have this setup. This setup code is to use to print stuff into the console. So first, move EAX to 4 means it's calling the system. It's basically system call number. It's calling system to write something. EBX1 is the file descriptor. Move ECX win message is loading the message into the the register that need to write stuff, that it need to write the win message. Move edx8 represent the length of the win message, which is 8. An integer 0x80 means the system will now call the kernel, and then it will jump to exit, which is another procedure. Down here we have lose. So the same thing as win. First gonna be move EAX to 4, which is make the system turn to write. Move EBX1 is the file descriptor. Move ECX lose message, load the message itself into a register to be ready to write. Move EDX9 is the length of the message. Integer 0x80, call the kernel, and then it will jump to exit the code. Draw for draw, basically everything here is the same thing as I explained in lose and win. EDX4 to write, EDX1 is the file descriptor, ECX to load the message, EDX is the message length, and call the kernel. And then finally, for the exit procedure, it move the EAX register to 1 is the system exit, and then XOR EBX to make it 0 and call the kernel. That's it for my part.